Okay, let's wait for him to join. Then I'll start. Let me also go and take a break before I come back. Okay. Hi, Yashod. Am I audible now? I think I am. Let's check. So, hello, Yashod.
Yeah, hello.
Yeah, I'm
Hello.
audible now.
Yeah, you are audible, but video is no. I can't see your video.
Can't see my screen. Seems, huh?
Yes.
Do you have any internet issue? Let me start reshare it. Let me see. Tell me how about now? Why don't I?
One second, I'll reconnect it.
I think it's better now. You can see my screen, it seems.
Yes, I can see your screen.
You can hear me as well. Let's go. Let's go. So I guess you missed the last class, right?
Yes, yes, I was in some.
Did you by any chance did you get the chance to
Yeah,
see what happened last time?
sir, exactly. I was not like last week. My health was not proper, so I could not.
That's okay. That's okay. You don't have to attend every class. That's fine. Just to give a brief background, that's why I was asking. Anyways, we'll spend some time in a small revision and then we'll go ahead. So, what were we doing for the last two classes were we were looking at finite approximation methods and yeah, and I guess you were there when we discussed finite difference. The last
Yeah, I
class
was
we
there when
discussed. Mhm.
when we were discussing final difference.
Great. So the last class we did finite volume. I specifically didn't start finite element because uh, the attendance in the last last session was a little low, and I knew that it would be better to wait another class, see if few people will turn up, and then maybe discuss finite element before. So before I go and do a small what do you say? So before I go ahead and do a small recap, do you what do you how well versed are you in finite element, if I may know? I remember you wanted to know what exactly goes behind finite element, but how well are you aware of finite element methods to start with? Some idea, or maybe not so much?
Hello.
Hmm. You can hear me, right?
Am I audible? Yeah, I
Yes.
can hear you.
Yeah. So I'm asking how well or how much of finite element methods do you understand before we formally get into the session? This is something that I wanted to ask.
Okay. So basically, like, how well in the sense,
It's
sir,
okay
I
if
know
you
that
know a very
formulation, how it is been done in finite element.
you
Yeah,
want to know or
basically,
you.
what the hello.
Mhm. Yes, I'm hearing you.
Yeah, the thing I was telling, like, the basic idea of finite element analysis, I have basic idea of that, like what
Mhm.
is being done and how it is being done. Basically, like we same as the finite difference, we separate this domain into elements, and we do this what weighted integration method to get the stiffness
Mm.
matrix.
Okay.
So yeah, this basically this little information I have because I have undergone through NPTEL course of finite element analysis by N.K. Tiwari.
Okay. Okay.
Yeah, yes.
So maybe some parts of it might seem too trivial to you, but what we are going to discuss today will at least help you clearly distinguish between the three methods: finite difference, finite volume, and finite approximation. Some parts may seem trivial to you, but essentially we'll look at the philosophy of finite element. As you said, a weighted integral method is going to come into the picture, and we'll talk a little bit about it. Again, this course is not intended on finite elements, so we are not going to go very deep. We are going to get an overview. Essentially, the same problem we did using the finite difference method, we are going to solve the same problem using finite element and see how it differs uh, uh, from the other two methods, finite approximation method. So let's get started. One last thing before we do that. Do you have any questions or something that you would like to discuss before we do anything else?
No question as such.
Okay, wait. So just let's start with a small recap. Um, for those who are watching this for the first time, I'm Shrey Sahai Gupta. I'm the teaching assistant for this course. We are having a series of live interaction sessions for this NPTEL course, and we're going to meet every Tuesday, discuss few things, and yeah. So we are going to discuss few things, and then let's this is essentially what it is about me. Uh, the first few classes, the first class was a glimpse into numerical methods. I have stressed upon it a little bit before as well, that while a lot of people might uh, might connect numerical methods with essentially finite element or finite approximation methods. Numerical methods in itself is a much bigger umbrella, with finite approximations only trying to solve differential equations, partial differential equations, um, or maybe ODEs as well. Yes, so now, yeah, but essentially these are differential equation solving methods. Numerical methods is a much bigger umbrella. That's what I wanted to say. We looked at divide and average method, Heron's formula in the first class, to see what a numerical method is. Then in the second class, on on the suggestion of other people or other students, I started with understanding finite and a series of three lectures on understanding finite methods. What we did was we took this 1D heat conduction equation. It is called a conduction problem because it has this double derivative term. So essentially, it's a differential equation, ordinary differential equation of second order. And for people who didn't, who couldn't just look at it and understand how where does this come from, we did the conservation of energy, formulated the conservation of energy principle to derive at this governing equation, and we were here. So this is where we start. Um for a broader purpose of generality, we even go ahead and non-dimensionalize this problem because essentially we are solving a differential equation at the end of the day. So why do we need to attach the connotation of heat transfer with this method? And if we do that, to remove that heat transfer picture of or frame of heat transfer from this problem, we can do non-dimensionalization. Once I do this non-dimensionalization, I have an equation of uh, double derivative of y in terms of x, and there is a RHS and there is a LHS. LHS is the differential operator there. Um, and then we started the finite difference. Before I go ahead and discuss finite difference, let me also show you guys the paper which I followed to frame the teaching material for these three classes. This is this paper. You can access this paper. Maybe I'll put it up. I have to do that. And this paper very clearly, very nicely explains how the three methods are fundamentally different. In fact, at one point, last class we stopped. We didn't actually formally complete finite volume method. So maybe I'll spend some time on that before I start finite element. But let me first start with finite difference method. The essential understanding of finite difference or the philosophy of finite difference method was. So, Yashod, can you maybe say what finite difference was all about? Like, what was going on there in
Yeah,
few lines?
basically, like, yeah, finite difference we used to take like discrete points,
Mhm.
like we discretize the domain and take to analyze like take the difference of the
Yes,
discrete points and analyze the required output. Like
great,
here in this example, it was like temperature variables.
great. So yeah, so you the key point, the key phrase was from your answer was the discrete points. The domain is divided into discrete points, finite number of points, and essentially what we are trying to do there is approximate the functional value at these points alone. So if after the method we intend or we need the information or if we need the functional value between two discrete points, that is in principle not possible. We can do some interpolation, but essentially what I'll show you that paper. So let's look at this graph. Okay, so essentially what's happening there, let's look at it. So first of all, let's understand what is this. So this is the error between the true solution and the solution given by the three methods. Black line corresponds to finite difference. Let's stick to just finite difference for now, although solutions to also finite element and finite volumes are given. Let's notice few things here. First of all, note how at the boundaries, the black line, the error on the black line goes to zero. That is because we enforce boundary conditions. Okay, that's important there. Another thing to note is, although we have not gone into finite element, we have gone into finite volume. What we see is boundary conditions are matched or are met in all methods. But let's look at And we look at only n equals to 5 case because that is a more coarse case, so errors are larger. What you notice is that between between nodes, you see the error is 0 at one node, and then there are 5 points. So one, two, uh, I think you can see my cursor as well. So one, two, three, four, and five. What you notice is the error is 0 only at the nodal point. So at the only the boundary conditions. Even at the nodal points, the error by finite difference is not 0, but it is low, but it is not 0. It's not exactly 0. Very upfront, very early in our discussion, we can notice that finite volume has a very small error in these cases. And that's true for even finite element. So you see, finite element is also closed. So if I go and look at the errors at nodal points, let's look at this one here. So at these 5 points, you see finite difference has some error. It has some error at these 3 points. Look at finite volume method. This the error. Wait. So actually, a direct comparison of finite difference versus finite volume is does not make sense because we noted in the last class that the number of nodes actually are different when you consider the same finite difference and finite volume. So because we don't have the 0.25 value of the solution at 0.25 with the finite volume solution in this table, at least let's not get into the comparison between finite difference and finite volume, but let's do a comparison between finite element. Where's finite element? I don't see finite element here. Yeah. So what we'll see today is, in principle, finite element ensures that the error is exactly 0 at these 3 points. We'll see that. That is how finite element method is ensured. So the first weakness of finite difference is that error is explicitly 0 in finite difference. It is not explicitly 0 for finite volume also at the nodal points, but it is explicitly 0 at the nodal points. For the case of finite element. It's not 0 for the case of, you see, the error by finite volume. So blue line is finite volume. This is finite volume. This is finite element, the red line. And this black line is the finite difference. So what the first thing is that we will see is finite element ensures that we get the very correct value, very exact value at nodal points. So that is something that we'll see today. That is one weakness of finite difference. However, there is then if we now start to compare finite volume, an important thing to note with the finite volume is that finite volume is actually quite strong when it comes to small number of nodes. So you will note that the error at between the nodes is quite comparable for both finite element and finite difference. They're comparable. But and so is the case with finite volume. That's true. That is there. But look at this in this range. At the boundary, the error at any given location very close to the boundary, the error by finite volume is much lower than the other two methods. That is another feature of finite volume. And we'll try to understand that once towards the end of this recap. So let me get back to our discussions there. Uh, my presentation. Okay. So as I told you, this is our scheme. What we do, what essentially by this discretization, what are we doing is converting the governing equation, which is which is a differential equation in a continuous function, making it a series of or a system of linear equations, which now in this week we have been learning how to solve. So then we frame everything as a AX equals to B problem, and then we just simply use those methods to find X or theta in that case. So nodal X contains the nodal values of the independent function. sorry, the dependent function. For the problem we had taken, we knew the exact solution, so we could actually compare how much error it there is, um, based on, compared to the actual true solution. Now, next session, next interaction session, which was on finite volume. The first thing that we noted was that was want, which we wanted to note was the difference in the philosophy of finite difference and finite volume. So soon you will see that finite volume also approximates differentials with difference operators or differences, as Yeshua told that we use difference operators or differences to approximate differentials. That's true for even finite volume method. But the interesting part is the treatment of boundaries. Rather than trying to find a functional value at a discrete number of points, we're actually solving the governing equation over a volume integral. And this volume integral is over a small control volume. So in some sense, we are essentially, so what that does is we start looking at fluxes. So if you know this term del square t del this term, you will note this is the differential of fluxes. This is the rate of, uh, it's not a rate, it's a gradient in flux, this term. So if you integrate it over volume, what you see is that this becomes a difference in flux. So difference in flux means flux in minus flux out, that kind of situation, and then you solve for it. Now the formulation of finite volume is such that these fluxes are conserved between control volumes. So what that does to our problem is that if essentially what you are doing is solving a conservative law, if not a constitutive law, if you're solving a conservative law, that conservative law gets exactly satisfied in finite volume, which is again not the case in finite difference. So let me show that to you. Let me go back and show how the fluxes, error and fluxes are there. So let's look at these three cases. Okay. So again, let's look at the table here. See, these are the fluxes. This is the flux. So because we have a 1D heat transfer problem, there is a flux at one end and another flux at the other end. Heat flux moving out of the boundary in the boundary. This is the flux entering in the bar, and then there is a flux at the left hand and the right hand. So these are the two in and out. And then there is also energy, what do you call, generation. This is a heat generation problem. So the right hand side has a heat generation term. If you go back and look at the problem, you'll see that. Now, over this entire volume, if you integrate over the entire volume, earlier finite volume helps, actually works by integration over a small control volume, small number of nodes. But in principle, any method, whether it is a finite difference or finite element of finite volume, the overall global mass, global balance should also be satisfied. That is one important requirement of any approximation method, right? So for example, suppose if you're solving mass balance in some pressure vessel, you don't want, um, say the mass, over time your mass in the tank has to remain constant, or it remains constant in actuality. You don't want, uh, you don't want, because of numerical errors, this you don't, just give me a second, just give me a second. Yes, so you don't want, mass to get, so essentially what will happen if there is a tank and mass is entering and leaving out over time. If your mass is not entering or anything, if there is the net mass flux in the tank is zero, so your pressure should remain constant. And suppose this is a long simulation, this is a long 10-hour simulation. Because of numerical error, if your method is saying that there is a net mass flux, global mass, entering into the tank, your pressure will continuously rise. Although the error can be small, but essentially you will continuously have an increasing amount of error. So a global mass balance is an important criteria in a global balance, not mass balance, global balance. So whatever equation you have, if you globally see what is happening, it should be exact there. It cannot be approximate there. Sometimes you require that, you need that requirement. Suppose you are working with a very coarse grid. There the error is supposed to be large, but you want very computationally effectively, you want the grid to be small, but you want global balances to be met exactly. That is an interesting, very important or very preferable um, quality, right, of a numerical technique. And that is the reason why finite volume are essentially very relevant in fluid mechanics and heat transfer problem, because essentially there we are solving a conservative law. We're solving conservation of momentum, conservation of mass, and conservation of energy there. And you will see that any fluid, even ANSYS, is based on fluid finite volume method. So that is one reason why finite volume works. So let's look at it, that finite volumes actually work. I'll just show that to you in the paper. So this is finite difference, the error in heat fluxes. There are certain errors. We look only at this table, this part of the table. Okay. And you see, as you go down, as you increase the meshing, the error will go to, error is kind of going to zero. Yes, the error is going to zero. So what columns do we need to look at? Let's look at this column. This column. Hmm. Let's look at this column. Okay. What you will notice is as you go more fine, your errors are going to zero. That's the good part of finite difference. You can essentially, it's a very low compute, like it's a very um, simple straightforward method. You increase the mesh size, you get closer to the solution. So that is there. Even finite element has issues with the global mass balances. Okay, so there are issues on the global mass balance as well. Not mass balance, global balances. But look at finite volume. Look at the error in this. So let's look at these three values. So this is the global balance which we were talking about. Okay, so you see that the global balances still have error in both finite difference and finite element. But look at this case. Numerically also, see, errors are there in individual terms. It's not that the errors are not there. But even with that error, you are essentially not violating the essential requirement of global balances. Obviously, it's not the perfect method. It has errors, but the global balance condition is ensured. So although your solution is off, but fundamentally, you are balancing things. Okay, so that is an important part there. We're not discussing how do we calculate this, because this will take some extra time, not required for us. We can just look at these results to appreciate the different as- advantages of the three techniques. So I just told you that finite volume works and essentially why it works. Let's also understand why it's working. It's essentially working because we are solving for flux continuity. So between two control volumes, the flux that moves from one control volume to another is ensured that it remains same. That is there in the formulation. And then these formulation is, see, this is just a, what do you guys say? This is like A plus B equals to C. This is the summation, right? This is a, not even summation, this is a addition there. So you see the fluxes differ by generation terms for every control volume. So if you look at essentially, what does that mean is that this will essentially um, ensure that if you add all the equations for all the control volumes, what essentially you will see is that these terms will start get cancelling. So what am I saying here? What am I saying here? Let's look at why global balances uh, do work there. So let's look at why it could work. So it will work. Suppose I start with the first control volume, which is E1. And then West 1. And then this is also 1. And then I just repeat this thing. Okay, let me just do this. You guys are able to follow me, right? Am I making sense?
Yeah,
Is
yes,
everything
yeah, yeah.
okay? Now, the important formulation, the important thing is that this is equal to this. This is an important feature of finite volume. So what essentially will happen? Uh, that these things that get cancelled. If you add these things, what you will see is uh, so this the flux in the overall control volume, and this will be the flux out in the overall control volume, and this is the addition of the thing. What you'll see is the global balance gets satisfied. Can any one of you answer why this does not work in finite difference? Can we think about it? Why will this not work? Why does this condition fail in finite difference?
Maybe because in finite volume we are integrating along the entire domain. So when we add up, so
Hmm.
the terms in
To
between
some
the
extent, yeah. Yeah. So let's maybe that's again I am also confused. Like not confused, but it's not clear as such why this should not. But I think we can figure it out. That's not a very tough thing to look at. Let's look at it. Okay. So why this fails? This is the finite difference approach. This is the finite volume approach. Okay. Why does this fail? Well, one reason is which we discussed is earlier was that um, the first reason could be maybe I'll look it up more properly the next time. But anyways, let's type. So one can be that the boundary conditions are not uh, or maybe let's say the governing equation is not enforced at the walls, resulting in incorrect fluxes. fluxes. So essentially, yes, right. Uh, maybe that could be a better reason. This will make sense, right? This makes sense. Yes. Yeah, that's the only reason. Do you guys see why this happens? So maybe I'll tell you. Yeah, I get it now. See, the whole problem, see, essentially we saw that for the inner nodes, if you would recall Apur, for the inner nodes, this formulation and this formulation was exactly same, right? And we can even look that up in the two codes that we wrote. See, the finite difference code had the same, these three lines were the same if you were the internal node, right? Now let's look at this one. See, I'll copy paste this, copy, and then I'll just paste it here. Let's see. See, these are the three same equations that we are looking at, right? So for the internal nodes, essentially the two methods are same, right? It's only the boundary that is making the difference, right? What you would recall from our previous discussion was the way we approximated the flux at the boundaries. You see, in a finite difference approximation, how are we approximating this term? How are we approximating this term? Can anyone tell me? Just by looking at this equation.
By Basically,
Actually, at the boundaries, the fact of the matter is that we do not set it or solve for this equation at the boundary, right? We just simply say that theta 0, theta x1 is theta of 0, right? Now, this is the way we do it. So, yes. So now what that does essentially does is, okay, yeah, that makes sense. So now what that essentially will do is, let's see. We say that, yeah, see, it's a little abstract here. Maybe I'll look at it up more properly, but it is a little abstract. See, the reason why, maybe I'll write this down. The reason why we get fluxes wrong in FDM is that we are not solving for them. We are not solving for them. Not solving for them. Let me check one thing. At volume, error is 0. Okay. Can you guys think of something? See, my logic here is that because we are not enforcing this at the boundary, is the essential reason why the fluxes are getting we are getting it wrong there. But then the question I am thinking of is then how come that we are able to get a correct boundary value also and boundary flux also at the boundaries? Is that something that is what do you say, reasonable? Hmm. How are we enforcing the boundary condition? Let's see. The way we are satisfying the boundary condition is here. We use this. Let me satisfy this. Okay. 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 Yeah, it's a formulation thing. See, mostly it's a formulation thing. See, let's let me briefly discuss this. See, in a finite difference one, we straight away just satisfied theta of 0 is 0, right? We just simply use that. And the fact that we did not enforce the governing equation, this equation. See, we do not have theta of xi minus 1 at the boundary node, or theta of xi plus 1 at the boundary node. In fact, leave that. We are not even solving for this governing equation at the boundaries. We are just simply saying theta of 0 is 0. So essentially between 0, the I equals to 1 and I equals to 2, uh, the solution that we are getting is essentially incorrect. That is the reason why we are getting a smaller error with finite volume. This error is actually much larger compared to finite volume because we are not solving for the governing equation in that region, right? Between this region, we are not solving for we are not enforcing the governing equation. We are solving for the governing equation at this point. That is why the error is the lowest here. For the finite difference I'm talking, we'll look at why finite element also has a similar property, but essentially in this part of it, we are not solving for the governing equation. And so we cannot expect the boundary flux to be correct. We are enforcing theta equals to 0 is 0, and that is why we are able to get the correct theta. But flux, there is no guarantee because we are not solving the governing equation in that region. I think that is the best I can explain right now. Okay, So that is there. Now, let's move ahead and see what we did with the finite volume. So essential, because maybe Apurv is here. Apurv, can you quickly say why, how finite volume differs from finite, or maybe we have done that. Let's move on. So now we understand that finite volume works by flux continuity and everything. Let's move ahead. We did the same thing. So approximated the differentials as differences. For the boundary fluxes, we had the Dirichlet boundary condition. So we used this double forward Taylor approximations to figure out the gradients or the fluxes at the boundaries. We did that, wrote everything as a set of system of equations, right? I think, yeah, like this. And constructed our A and B. This is where we started the finance. We construct our A and B here. Go ahead, solve for it, and we see the finite volume is also correct. Okay. In fact, let me see if I can quickly also plot finite volume. So n equals to 10 and n equals to 10. Or n equals to 5 is also okay. Yeah. Right? Let me FTM, right? So let me XFTM, comma theta FTM, X, comma theta. This is what I did. So roughly almost same. Let's see what happens with 3. 3 would be nice here. And this one with 2. Going a little fast, but let's see. See. Happened here. XFTM. Yeah. So what's wrong here? Yeah. Yes, yes, yes. So boundary. See, this is the difference there. Curve is 0. Okay. Good. Yes. So let's see this. Maybe I'll also do this. X equals to 0 plus to list. So this part of it, whatever I'm coding, should I discuss that part as well? I think not required, right? Uh, Maybe I'll discuss that. You can just let me know because I'm going a little fast here. Just wanted to show you a little bit of comparison of the two methods right now. Eta dot to list. So what I'm doing is appending this, because see the way we have defined our x in our finite volume method is that we are not defining at x equals to 0, right? X equals to 0 and x equals to 1. Like last time we discussed that. So I'm just adding these two values to the list just for the plotting purposes. Let's see. Yeah. So you see how finite volume. Hmm. Let me do this. That But very low values we can actually see what's going on here. Yeah. So you see finite difference and finite volume is actually kind of more like at this point. Maybe I can try with 4. Let's try one last time. Just go ahead. Yes. Or just 3. I think that's better. Right. See how finite volume and finite difference have different values. Um, different values. What you should note here is I'll also mark here. Actually, the locations of the nodes and the nodal values are actually different. They're a little shifted by delta x by 2 value. So that's why this is happening. That's also interesting to see. Color, I'll do a C5 maybe, just to see. Mm, that should be at the finite volume. Finite difference. Yes. See how finite difference marker I'll put here also. And the difference will only be like you can observe the difference. Okay. So the exact solution is the green part. Okay. Maybe what I'll do is I'll do that. Just give me one last minute to just. Okay. Let me define this XXZ to be dot in space 0, 1 and 100. Let's do that. Okay. I think that's better. Yeah. And I'll also increase the line width here. Or maybe there's no point. Let's see. So you see the exact solution is the green line. Okay. And this one is a little thick. Okay. And you can see that finite difference and finite uh, volume are getting different solutions. But at the nodal values, they are quite close to the, what do you say, to the exact solution. So they are not very different. Okay, at the interior nodes, actually at any nodal value for that matter. Okay, so that's there. Now let's go ahead and discuss the very awaited finite element method. Okay, let's do that. Okay. Right. Okay, so let's get started with finite volume. So finite volume method, finite element method. So any doubts, guys? Were you able to follow that coding snippet, or did I just do it in my own head and you were not able to follow it? Any questions about that?
Sir, one request I wanted to make. If you could discuss Thomas algorithm and other iterative methods also, the coding part. Uh, so
The
because I
algorithms, right?
yes, yes, sir, because I'm very new to coding part. I can understand the theory and all, but I find somewhat
Oh. You said Thomas algorithm. This is the tridiagonal method.
Yes, yes, yes,
Tridiagonal method.
yes, sir. Those
So,
things.
and
Or
this is
even Gauss
Yashod.
seidel, those things. Gauss
This is
seidel.
Yashod, right? No, Apur. Apur, do you want me to discuss this thing? See, I can do that. Sorry, I'm typing Apur. TDMA. Yeah. No, no, this is not that one. Thomas algorithm. So, Apur, actually, the way we can do it is this is the solver. This is the LU factorization, right? So maybe I was thinking those things are actually pretty trivial if you ask me. Essentially, you want me to solve AX equals to B, right?
Yes, yes. I just want to, if you could just go through the code part, how to
Okay.
write at least the
Right.
pseudo code.
That
Pseudo code is fine. The code part only.
okay. You want me to discuss that, huh? Okay. Let me see. Can we do it? Can we do it using Chat GPT and just let's see what are they doing?
Okay, sir.
That will be quick also. I don't have to write the code entirely. We can just quickly discuss what is going on there. Okay. Okay, so first see. Let me first open Thomas algorithm. That's the only algorithm you want me to discuss, or what is it?
Gauss seidel also.
Gauss Seidel also. Okay, Gauss Seidel, Jordan. Let's see what all algorithms are there. Mm, okay, let me.
I think these are the only ones, right? We employ in all the codes for
So
like sorry,
so if
flow
you ask
paradigm.
me, what do we actually use? If you ask me what do we actually use, I think we don't use either of them. Let me see. We use. So what does this use? So this is the Python library function that I would generally use, okay, to solve this AX equals to B thing. Now let's go through this documentation to see what is going on here. What are they using? If the data matrix is known to be a particular type, then supplying the corresponding string chooses a dedicated solver. So there are several solvers here, okay, and depending on your matrix, you can have different solvers, okay. That is one thing. Let's see what kind of solvers they have. If the input matrix B is a 1D matrix with n elements, okay, the general symmetric Hermitian positive definite solutions are obtained via calling GSV, SysV routines of LAPACK, respectively. Okay, so what is this general GESV? LAPACK. What is this? This is the general solver, okay. There can be better, like more efficient solver like HESV or POSV. We'll have to see what are these formula, like what are these for full forms. But GESV, what is it? GESV. So LU decomposition only. What is GESV? Actually, Apurva, I'll suggest you can quickly go through these things in the time of AI. Quickly, it will explain everything to you if you want to that part of it. Okay, but let me just check. So what is GSV? What for GE matrices? So what are GE matrices? General Electric matrix. No. What is this? General matrix. So basically a general matrix. What is this linear solver? General matrix. Let's look at this. Let me ask ChatGPT itself. That let's see. Let's demonstrate the power of AI in figuring out simple things fast, simple things fast. Okay. So what does scipy dot solve do is to solve ax equals to b. The function delegates. Okay, under the hood. Okay, fine. For general dense, you use LU decomposition. Okay, so you use LU decomposition. Have you gone? Have you finished LU decomposition there?
Yes, sir.
Okay, so that's what you do. Okay, can you write quickly? Can you write LU decomposition code for me? Of course, let me get. I'll have to go through this part. I'm not sure. Let's see. Hmm. Okay.
Actually, I asked you, sir, because in MATLAB also like all the uh, so, linear equation solvers like a backslash b and all those are also based on these things only, like Thomas
So that
algorithm.
yeah, that's my whole point. If these things are there, why would we write our own code in the first place? We just need to understand what's going on, and that's the theory. We can go and do a hands-on coding session. We can do that. We can code the same thing again, but that solves. I don't know if it solves anything. It might. It will give you a little practice. Maybe some parts of the theory you might not be able to understand. But yeah, let's see. Actually, that's a good point. I thought that it is it's a simple thing, especially classes or like lectures are also there. So I thought that we'll discuss these things which are a little off the course content. So we want to factorize our matrix into a lower component, a lower matrix component, and upper matrix component. How do we do it? So can you tell me the theory of it? I'm not sure of this theory. I've not gone through this for the lectures thing. Can you quickly go through what's going on?
For LU decomposition. Yeah, we
Yeah,
take a pivot, then we factorize, then we subtract from the lower equations from that. So simple arithmetic operations, that is okay.
yeah.
I wanted to ask, like, say we have a tridiagonal system. So how do we create the matrix for that in order to solve it?
So let's look at Thomas algorithm for that matter, right?
Yes, sir.
Okay. I think Thomas algorithm I remember partly. Even Gauss Seidel is also there. TDMA. Let's code TDMA. So let's code TDMA.
Like, how do we store the values of the matrix? It's a sparse matrix, right?
Okay. Okay. Do you want me to do that in MATLAB?
Yes, I just okay. I'll see in ChatGPT how it what it is. Maybe just you
No,
can just run through brief.
he'll quickly go through it. Yeah.
Yes,
Let's see. So what we are doing is we are solving TDMA. TDMA is what? What is TDMA? We have looked at a TDMA, a tridiagonal matrix before. In the even for in both of these equations, look at what A was.
yes, sir.
Apur, can you look at, you see how there are only, because every node is associated with only neighboring nodes. So
Yes, yes.
essentially whatever matrix you'll get it will be a TDA, a tridiagonal matrix. Now TDMA, that's one thing. Now what are we going to do? So they use copy arrays to avoid modifying original. This is okay. So ABCD. What is ABCD? Sub diagonal, main diagonal, and super diagonal. Okay. This is also quite easy, right?
Yes, sir, that is okay.
So these three diagonals we have inputted the three diagonals, and D is the RHS vector, which is like B for us. So if I would like to rewrite my own code, I will say lower diagonal, upper diagonal, a main diagonal, upper diagonal, and B. I would like to use it like this. And what I'm essentially saying is, I'm saying A equals to mm, like this. Maybe I'll do it there. Before I do this, let's quickly do TDMA. Okay, so A equals to, I think most of it you understand, but still. Essentially, we will have diagonal, 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 and so on. Then there will be upper diagonal, lower diagonal, lower diagonal, lower diagonal, lower diagonal, and then upper diagonal, upper diagonal, upper diagonal. Okay. You feel the need for me to go like do this an upper diagonal.
And just creating the matrix, how the values are stored, please.
Okay. Okay. So now once so we understand that there will be a lower diagonal, there will be a main diagonal, and there will be upper diagonal. Matrix, or the number of points you want to find the values of, which is the length of our RHS vector, which is AX equals to B. So AX equals to B, that kind of thing. Okay, we'll just change the code here. Now, what are we going to do? Copy arrays to avoid modifying originals. So they're just copying them with a map. Okay, so let's look at how this map works in Python. Let's look at what this map does. Map of 1, 2, 3, 4. Let's see. It must have at least two arguments. Okay, 4, 5, 6, 7. So what it will do is it will connect every. See. So how do I visualize it? Let's also look at how do we visualize a map. So what essentially is this line doing? Okay. Let's quickly copy and see. Okay. What is this map doing? Let me just quickly look it up. Okay. So now in this case, what have they done? Let's see. What has this guy done? So before I do that, let me see if this code works fine or not. Okay, that also we'll see. Okay, this one is working. Yeah. So what is this TDMA doing? np.array. Okay, fine. So this map is doing nothing. That's a stupid proposition. See, what is this doing? This is in Python. This is a list. Okay. Apurv, just hear me out here. This is called a list. Okay. Now, list is a simple data type. This is a primitive data type or a fundamental data type in Python. You might have a similar thing in MATLAB. But in Python, there is a extra library called NumPy library, which allows you to do these kind of operations. See, I'll show you these kind of operations. So what will this be? This array be? Will be this. But now I can multiply this array to twice. The same thing I cannot do here. See what happens here. A list gets concatenated if I do these kind of things here. See, if I do this here, what will happen? First of all, it will not allow me to do anything. This is the operation I can do. If I want to do something of this sorts here, it allows me to do this. So this is just a simple like a library of storing arrays. This is just one another way of storing the same thing. Okay. So what is this doing is this is just saving the thing once again. Okay. So we'll also do the same thing. Instead of doing this, let me do this. Uh, uh, so upper diagonal. So lower diagonal one is np.array diagonal. I'll just copy paste the entire thing. So this is that one line was doing the work of this these four lines. That is what it was doing. Main diagonal. This is upper diagonal and then B. And we are just saving a copy of all four of them. Okay. If you're able to follow me, just let me know. If you're not able to follow, please tell that as well. I'll properly explain this. There's no problem in that. Okay. Now what are
You
we doing?
vectors, like, right?
Vectors. In
Yeah.
MATLAB, huh?
No, in this also, like LDL equal to numpy dot arrays. Yeah, that's a vector.
Vector, yeah, you can call it a vector. I like to call it an array or a list, but yeah.
Okay, sorry.
Vector, why do we not? Why do I vector if there is an issue? Vector. No, there is no issue. Yeah, there is no issue. So this is the upper diagonal vector, lower diagonal vector, and main diagonal vector. Yes, that's right. Okay. Now what are we doing? What is this part of it? This is called forward sweep. Let's look at what forward sweep is. So do you know what forward sweep is? Can you tell me?
Uh, Forward sweep, like, I don't know why what it is actually in this code, but in
Okay,
TDM, like what we know is like Gauss elimination only. We try to eliminate the points below the pivot.
right. So there's a pivot and it starts from the lowest row to and it moves up, right?
Yes.
Okay. So what are we doing here? Let's look at it. Um, so
Especially in Thomas algorithm, like the diagonal below the main diagonal, we try to make it zero. That's the
right,
catch.
great. And that is what the Gauss seidel is also, right? No, Gauss seidel is different.
Gauss seidel is
This one
iterative
is
method.
also oh,
No,
okay, got
this
it.
is not
Got your
iterative.
point. Got your point. Got your point. Understood. Understood. But this can also be iterative for that matter. Anyways, yeah. Okay. So essentially, what are we doing here? Let's look at this column. Okay. Um, are we doing the same thing here? What is AC, BC, and DC? Actually, I ruined it. Let me see what is AC, BC, DC. AC is the lower matrix, right? Subdiagonal. Okay. And then BC is the main diagonal. O- Okay. So yeah, it stores it like AC and BC and CC. That's the standard form. That's fine. What are we doing? We are saying X of, are we saying anything about X? No. Saying BC. This is Gauss elimination only. Okay. Let me think. What are we doing? First sweep eliminates AIs. and then backward substitution produces the solution. Okay. So what are we doing here is this is lower diagonal. This one is diagonal.
All the A's are made 0.
Uh-huh.
All the A's are made 0 here. All the
Yes.
A's, the lower
So
diagonal
first
is.
of all, we are storing dividing this we're finding an by bn, right? Here, the first this line. This is an by bn. Let me write that. An by bn. Is that okay? Then this one is d I. What is dc? Just another second. dc b. This is bc. Okay, got it. So yes, this is b and this is b. I like to do it this way. This is also d. This is b. So what have we done here? This is also upper diagonal, and this is also so maybe you can just see how can you go through one way of looking at it. Okay, how do I quickly go through this algorithm? Okay, so this is what it does. Copy arrays, that is fine. Now forward sweep. What is it doing? Eliminating AI, as you told, the subdiagonal. What is the step? Ratio of the subdiagonal to the main diagonal. This is this line. Now update the main diagonal of the current row. Update the RHS. Okay. In hmm, in LA in linear algebra, tell
In
me.
that I understood, okay, what it's trying to do, but in the
Hmm,
code I can't see where it is like storing, allotting the values or storing the values in the matrix. The code
okay,
is
let
written,
me.
that is fine. Uh,
Okay,
Say like in flow problems we can have 1000 by 1000 order of matrix. So how do we store these many values? Like how do we write the code for that?
okay. So what I see from the code right now, actually we don't need to make a whole matrix to solve a 1000 by 1000 case. What essentially we'll do is make a 999 to 999 cross vector of length 999 and 1000 length of 1000 values, right? That is what a tridiagonal matrix can be expressed as a set of three vectors, right? Is that clear? First of all,
Ah, yes, sir, that is okay.
that is
Three
okay,
values.
right? So we don't need to actually store any a in such, like we don't need a 2D array to have TDMA, right? That's first.
I was thinking that way. I was thinking that way that we have to store the values in a matrix, 2D matrix, then we do all the operations.
No, there is no. So we'll see why there is no point. Essentially, in an abstract sense, there A is having A, B, C, D, and so on, but we don't need them. Don't need to, because as you told me, the matrix is sparse. We don't need to store it, and um, by our what do you say, our manipulations, we can just, because now we have an algorithm. See, so let me just see that. So what essentially is are we doing? What does forward elimination doing is W is this is equivalent to Gauss elimination. Okay. Uh, what is the linear algebra operation of Gauss elimination? So transform the matrix into a upper triangle form. How do we do it? We do it using row operations. Okay, right. So can we look at it from a matrix point or matrix operation point of view? Okay, so as far as I understand it now, what are we doing? See, you have ax equals to b, right? You understand that, right?
Yes, yes.
Okay, now suppose I find in some by some magic, if I find a transformation, or if I find a matrix which, and I multiplied that matrix on the both sides, so that essentially what I have is a dash becomes this, right? And then this is a diagonal matrix. Suppose this is essentially what we want to do finally is a diagonal matrix, right?
Yes, sir.
So x equals to, and whatever that eigenvalue will be, we just divide it by the corresponding value in b. Like, so suppose 5x equals to 4. So we just say 4 by 5. So essentially you want that form. Now, what we'll do is the algorithm says that you do a forward sweep. This is the algorithm. You do a forward sweep. Let's go through the algorithm. So what you do is that this is the algorithm that we need to see. So we need to do the Gauss elimination thing. We swap two rows first of all, then multiply a row by a non-zero scalar. That's okay. We do like this kind of stuff we do. Um, what kind of what what book are you following, or what which lecture? Can you tell me which lecture do we are we looking at? Lecture number? Can you tell me
Uh,
that?
Let me check, sir. 1 minute.
Just yeah. Let's quickly look at the lecture number. The one. You know the lecture number, huh?
1 minute, sir. Let me check. TDM is lecture number 77.
Lecture number 77.
Yes, sir.
Oh, 77.
Yes, sir. Yes.
Which course is this? Which week is this? Pur?
Yes, a week. That will be, I think, seventh week, sixth or seventh week.
We're not there yet.
I thought, sir, you were discussing finite volume, so I thought of asking that.
Okay, let's do this. But we are still ahead of ourselves. But okay, that's okay. So I'll just look at the part where Sir mentions the algorithm. Okay, so see how he has done this, right? You see, let's just simply look at what we are doing. So what we'll do is our xn will be dn by bn. Okay, the same thing that this I'll go back to the code that this guy has done. Not not change. I changed the code for my convenience. It's not good. This is the code, right? Where is the code? Hmm. Okay. So you're following this, right?
Yes, sir.
Okay. So what does it say? Let's go first back. So these are all zeros. That is fine. Now the first thing we do is, yeah. So the first thing we do is, see, you convert every entry, every main diagonal entry by this operation you do, right? You convert bi, you subtract bi by ci into r. Now what is r? R is a ratio. Okay, r is a ratio. Wait, it does not say what r is, right? Just give me a second.
Ratio, sir. Ratio.
Which ratio is it?
Mainly it will be like if you are taking say if you're taking A2 as the pivot, so no, sorry, if you're taking B1 as the pivot, so I think it will be A2 by B1, something like that, or B1 by A2, in
Do
any one
you,
of them.
does it say? Let's look at it. Let's look at the thing there. So you have a pseudocode with you?
No, sir. I one.
See, see, Apur, this is the equation that we are looking at. Rather than looking at simply Ax equals to B, we start looking at like this. So set of three, what do you say? Three dot products. So vector. So these are dot products, right? So Ai is a vector, xi minus 1 is a vector, bi is a vector. These are dot products. That makes sense?
Yes, sir, that way we can write.
Yeah. So that is one thing. Then what do you do? The forward sweep consists of computing new coefficients. So what you do is you can first of all divide ci by bi. This is your ci dash if I equals to 1. Otherwise, what is ci? See, we are forwarding, we are not looking at I equals to 1 case. See, in Python, the first element starts with 0. So we are looking only at from 1 to n. Okay. Now, is that okay?
Uh,
So I'll show that to you. Suppose there is this array of, tell me one array. Let me say 1, 2, 3, 4, 5, 6.
so
For
the
I,
indexing starts from zero. Yes.
hmm?
The indexing, I think, in Python starts from zero, right? Yes.
Yes, just show that to you. So this one, you see how it starts from 1. If my range is from 0 to 5. Okay. But if my range is from 1 to 5, you'll see I'll skip 2. I'll skip 1. I'll directly start from 2. So essentially, in this set of operations, we are going to operate it for this part of it. Can you see my cursor? Whatever we are doing is for these number of entries from 2 to n minus 1, first of all. Now what are we doing? We are first dividing C by B. Okay. And then we are writing we're also substituting SC. Look at it. For I equals to do this. You do this. AI by BI minus 1. Wait. This is, hey man, come on. What is this algorithm? Yeah. So look at it. Uh, so Apoor, do you have some example problem? Do you have a B C kind of setting? Or let's look at this finite difference one only. Let's look at this one only. Okay. Let's look at this. This is our so what is our upper diagonal? What is our lower diagonal? And what is our this thing? Let's look at this. Okay.
Yes, sir.
So from using this matrix, can you tell me what will be our A? Will be 16, 16, 16, 16, and 0, right? The sub-diagonal matrix. NP dot array. Then we have 1 minus 32 minus 32 minus 32, 1. And then C will be NP dot array Can you tell me now?
I think 0, 16, then
16 and
16,
16.
16.
And then we'll also take the D value also. So D value is here. This is the D value, right? Yeah, this is our D values. Okay, fine. So this is our D value. First thing. Okay, now okay. So now what do we do? See how the solution is becoming 0 and 1. So at least the boundary conditions are satisfied. That is one thing. And another thing is here 0, 1, 1. Okay. So now what do we have to do is the algorithm says, so I'm just following the pseudo code here, okay? We'll also open this book. The book will be fine, perfect for this thing. Thomas algorithm. That I have a credible this thing. Okay. Right. We got it. Good. So notice that we have changed the notation. Figure 11.2 shows a pseudocode for the efficient method called the Thomas algorithm, okay? Which is figure 11.2. So choke CD composition. No, this is figure 11.2. Do you see where figure 11.2 is? I'm not able to see. Yeah, this is the figure 11.2. Yes. So what do we do? This is the algorithm. Let's look at this algorithm. Do for, I don't know what this do for is. Okay. So for k equals to 2 to n. Okay. What we'll do is we'll first find ek. What is ek? Subdiagonal. So just look at it, how our subdiagonal value fk is the main diagonal. Okay. So see, I said, so should I go ahead and just implement this pseudo algorithm? Apur?
Oh, yes, sir, you can.
Okay, so what are we doing? See, here it says, so let me exactly follow this algorithm. Okay, so ACI in range 1 to n. Okay, so we'll first of all see, rather than we'll not even use this, we'll just remove this. We'll move from 1 to n. That's okay. We'll say AC of I is AC of I divided by BC of I minus 1. Okay. Then BC of I, which is this main diagonal, is BC of I minus AC of I. So you were able to follow this first line for line number 15 from this 1-to-1 correlation. Let me do one more thing.
Yes, sir. Yes, sir.
You're able to follow it, but let me do
Yes.
one more thing. EF, G and H, I guess. G and H, right? EF, G and R. EF, G and R. This is the nomenclature we'll follow for time being. Okay. EF, G and R. N will become the length of R. Okay. Now for I in range K. So I or let me use K here. K moves from range So just to make sense, let's move. So in our case, what is n? Uh, Apur, you can be online, like you can be unmuted for some time now. Let's do it together. So what is n in our case in this example?
4, right?
4. Okay. Yeah. Shift. Let's see. So I have just plotted this entire thing. And also I'll stop this. So see, I have plotted what I will be in this loop. I goes from 0 to 4, right? What do we want it to go from? We wanted to go from I will take k as I plus 1. Okay. And this I will do -1 and I'll print k. So it will go from 1, 2, 3, 4. Okay. Or maybe let me do this also. So it goes from 2 to and this is 5, not 4, 5. See, our length of you can unmute yourself. Sorry, there's a little bit of echo. So we have 5 points rather than having 4 points. So it goes from 2 to 4. So we are printing k plus 1 here for our convenience, just to show that to you. But here, because our arrays are like this, so what I'll write is ek is ek by fk. That's the first k minus 1. Then fk is fk minus ek into g. That says g, yeah, gk minus 1. This is the first thing that we do. Finished. Okay. Then we'll do, so this is the decomposition phase. Now, and this is how we do run the loop in Python. Now we'll do a forward substitution. Again, for I, similar thing. Rk is Rk minus Ek into Rk minus 1. I'm just following the algorithm right there. Nothing much to be done there. Now let's look at backward substitution. So now I need to write x. So okay, now because we need to store the values of our whatever we are going to find, let's do this here. This is the array where we will store the x values. Now I'll write, maybe I'll remove this. This is entire thing we are writing it again. Okay, so for xn, which is x minus 1. You get that, right? Or you want me to write n minus 1 x r n minus 1 divided by f n minus 1. You are able to get why n minus 1 or no?
Yes, yes, sir.
You're able to get it, fine. Now again, we'll do it from
Like I have a question, sir. One question.
Mhm.
Like
Please.
you are doing all this for this matrix, right? Six. So do we have to like always whenever we are solving a problem like a very with large number of equations, do we have to like manually create all the arrays, right? Say if there are 100 by 100 problems, so do we need to like make an array manually of 100 elements? That way do we have to do, or there is some shortcut for
Okay.
that?
In your case, so you're asking me, but tell me one thing. How are you getting that array?
So, like, say your one day conduction problem is there. Say you want
Yeah.
to discretize with.
So how did we do it? So how did we do it? Let's look at that code. Okay. So first of all, I didn't use this thing. Okay. So let's see what this does. This is the function that I use. You can,
You
I
are
think there is a,
initializing it, right? Like,
yeah, we are kind of making space for it in the temporary memory. We make a space. Okay.
hmm,
What we could have also done is ones. This is also a function, but essentially we know most of it will be already zero, so we use this function.
yes.
Okay. Then we start traversing in it for I in range. See, and then we make this tridiagonal thing. A I minus one. So these are the we could have also done this. Well,
Yes,
this
wanted only this part only. So yes, sir.
this part only, right? So we could have
Yes,
done
yes.
this. Suppose if I don't want to do, instead I want to save this as three matrices. Let's do that. So what I'll do is I'll make A, B, C, D. Okay. What I'll do is I'll say BI is one. So this line is gone. Okay. Now I'll switch this off. I'll write BI is one. Now tell me if you understand this. Cool. Do you understand that?
So there should be two indices, right? Like we are creating a 2D matrix. So like
Yeah.
below that you have written AI minus one. That those things I can understand. But why here only you're using only one index?
Because as we mentioned, see, look at this matrix. Look at this matrix. There are only three diagonals that we need to store, right?
Yes, sir.
You need to only store these three diagonals. So you can actually represent them by three vectors E1, E2, E3, and so on, isn't it?
But we when we have to solve it, we have to solve it in the form of a matrix, right? Then only we do back substitution, all that.
See, no, 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 no. So see, that is where the Thomas algorithm is coming in picture. You don't need to store the matrix in the first place. You don't need to do that.
Hmm.
That is what that you don't need to do that. By actually, you're trying to bypass that entirely. The whole point is that see you are writing the code behind this a and axn plus b. So whatever, suppose you are a engineer, like you are a software developer which is trying to write this library which solves ax equals to b, and now you are given the task that suppose I already know that this matrix is a this matrix is a tridiagonal matrix, suppose. Then how do you solve this? Okay. Now, because you are in charge of the code of your cells, you don't need to store it in a matrix. What's the point? Save, if you can save the space, you can just simply store vectors now. And at the end of the day, you are simply whatever you're doing is doing vector manipulations. You're not doing any matrix manipulation at this point, isn't it? In the entire pseudo code, do you see anywhere where you need two indices? See RK, XK, GK. You can work with the algorithm is such that you can work with vectors only. You don't need 2D matrix in the first place.
That is the
That is,
point.
Mhm. You were saying something.
No, sir, I just said that yes, sir, that is a valid point that we are only dealing with the pseudocode has only one index. That is yes.
That is one index, and the whole point is that because the matrix is three-dimensional. See, we have to note that there is this. How does the problem reduce from two-dimensional to one-dimensional? You have a legit question, but the answer to that is that we have separated the two-dimensionality by dividing into three different vectors. That second
Mhm.
dimension is coming here. by differentiating between vectors. E and F are two different vectors now. So in some sense, you can think that E moving from E to F to G is the second dimension. So
Mhm.
essentially, you're still having a set of vectors, just like how you did when you had a 2D matrix. Now you have three vectors. Instead of having a full-blown 2D matrix, you're having three vectors. You got it?
Mhm.
So,
Yes, yes.
okay. Then we can also do this. Ci is again this thing. Okay. And then di also I will write. What is di? Di is this. Then d0. Then we'll also write d0 is 0. Wait, I have to do that first. Think d dot append 0 and d dot append 1. And this also has to be appended. See, we are now working with lists. This is a different lists do not work like IN because there is no index. I don't want to confuse you. That's why I'm just simply writing it. Okay, just don't get confused. This is exactly the same thing that what I just wrote is the same thing. It's just the code won't work otherwise. We have to do this. So now let's see what A, B, C are. This can be N can be what? N can be 5 or 4 maybe. I don't know. Del X can be what? Let's look at A, B, C, D. See, how did we get this? At least this part is clear. Do you get that?
Yes, sir.
Or
I'll
no?
just look at. I'll check that what this thing you have used happened. That thing I'll check.
What will you check? Or do you want me to move on, or do you want me to stick to this part of it?
No, sir. Can you just tell me what is this app and thing? NumPy, I
Ah,
know. That.
okay. Okay. I'll tell you. See, in this list one, okay, I'll tell you this. In Python, what happens is that there is a provision because suppose we don't know how much space in see in Python, suppose you don't know a priori how much elements you will have in your matrix, in your vector. Okay. So you can do it like this, 1, 2, 3. Okay. Now suppose at some point of time I feel that I need another element to be added into this. So what I can do is I can do this. Okay. So I'll show it to you, print list, and then I'll print list again. Important thing is that list is a keyword in Python, so you can't simply use list. You have to use a different name. So list underscore I have taken. Okay, and then you have to do this. See, did you see 4 could be added here?
Yes.
I'll tell you another method to do the same thing. So this will be list dot append 5, and then let's print list again. Sorry, this should not be there. It should be simply this. Let's see. Did you see that? There is another method. Actually, this is the same thing, but there is another method. I'll show that to you also. So this is just a syntax kind of thing. This is a language specific thing. Okay, if you do append, this will happen. You see, the next element after 5 is not 6, 7, 8, but it is an array of 6, 7, 8. So we use this function. If we want to store multiple values together, we use this extend. This is something that you cannot do in NumPy. See, A or say A equals to np dot array. When you define it, you need to give me the length of it. You can't increase it. Okay. Uh, it might be cumbersome to do it. Maybe you will have to use np dot concatenate and something like that. Concatenate. Oh, 3. np dot array. Actually, I have to save it like this. This has to be again numpy. See, so it becomes a little tricky there if you don't know a priori how many values you need. In your case, a dot concatenate or what? Something is there. I don't remember this part of it. Let me check. Some this thing np dot concatenate or something is there. I don't remember exactly. In your case, we could have started with this. Okay, let me just show that to you quickly. We could have started with this numpy dot zeros n. Okay, here we need 4, right? And then we could have had done this. Okay, let me show that to you. And we could have also done that. That there is no problem there. Then here you do this thing. D0 is 0, and then D1 is D minus 1 is what is it? 1. Print. We could have also done that. Same thing. What is it? It's wrong. N minus 1. See? So 0, 16, 16, 16. See, it's the same thing. So print ABCD. Okay. See, and look at this. Oh, something is wrong. So it has to be, in this case, it has to be AI plus 1, because yes. So it has to be like that. So A has to be A0. So this has to be AI plus 1. Okay. And this one is okay. Just give me a second, just a second. So these are 4 values or 3 values? 3 values only. Yes. Okay. See, there is another incorrectness is there. Some issue is there. CI will also be outside. Still be outside. So now problem remains to be, this should be correct. This should be 16, 16, 16 and 0, and this should be 4. Let me think what's going wrong. You get what is the issue here? See, with this, because it becomes a little tricky, isn't it? Here it became straightforward. See, 16, there were 3 16 values. 3 16 values. Here a 0 will be there, here a 0 will be there. Or still confusing? Still confusing, right?
Yes, sir.
Okay. So first of all, let's see what are our diagonal matrices. Okay. Our our main
The
diagonal will be will
your older code was good, sir. That one I have some insight into the thing.
this
The one
one.
which you, no, sir. The other one, I mean, the one which in which you had used two indices. That is quite clear now. Yeah,
So
yes, this one is okay.
this one is okay. You understand
Yeah,
this.
yes, sir, this I can understand.
You're not able to understand this one.
No, yes, sir, that one I'm not very clear.
Okay. So Apur, you need to understand one simple thing. Then this becomes very simple. This is not nothing new. Okay. Suppose in see these are I'm having two indices.
Hmm.
Okay, let me do this. Let me do this for you. Let me just do this for you. And what else? Let me with this we'll close for today, but let's just quickly do this so that at least this part of it becomes clear to you that these two things are equivalent. This is clear to you, right? What is wrong here now? A and B, huh? Let's see. Let's see if this becomes clear to you. This one you were happy with it, isn't it?
Yes, sir.
Okay. So what we'll do is we'll just use this. For the sake of our like consistency, so that it does not become again challenging or again confusing, I will define four vectors: ABCD, small ABCD. Is that fine?
D is what, sir? Here, D is
I'll tell you.
right, right
So,
hand side.
or let me do this: FGHR. Sorry, EFGHR. EFGR. Now look at this tridiagonal matrix. Now, is up till this now you're okay?
Yes, sir. Okay.
You're okay, right?
Yes, sir.
Now the rule is that main diagonal matrices value will go in F. That much is clear?
Yes, sir.
Okay. So what I'll do is Fi, because see, now I'm saying Fi. What do I mean? AI I, which is like let me write this first. This is essentially saying that the first A00 or A last AFN or F1 is this. Is that okay? Do you get this?
Hmm.
So I'm saying F either if it is F1 or if it is Fn, then I will store 1 in it. This line is okay.
Yes, sir.
I'll also say this, or let me say this. Let me say this for I. This AI you understand, right? Now what I'll do is for I, Fi is I. EI is I minus 1. GI is I plus 1. RI is BI. Now tell me, will this code work if I run it?
Should be working, but
No, there is an issue.
the
If
index
I
has to
is
be
greater than
the
0,
index.
then this will work. And if I is less than n minus 1, then this should work. Now let me check once. No, there is an issue. If I is greater than 0, what is the issue? FII. This is range 1. Okay, so it worked. Let's see what is F, what is A, See the main diagonals. A1 minus 32 minus 32 minus 32, and then 1 didn't happen. Why did 1 not happen here? Because this is n plus 1, it seems. Okay, so this is what I need to do there. There. The issue is because of the now see, look at it. Now look at the main diagonal and F. You understand that, right?
Yes, sir. But for using this, you have to define it, right? Like fi equal to aii, ei equal to
I'll get to
ai
that.
minus one.
I'll get to that. I'll get to that. You're right. Right now I am defining it. AII is defined. You are right. But however, you understand the logic here, right?
Yes, sir, that is okay.
That is okay. Okay. Now also let's look at G also. Look at G. 0, 16, 16, 16. And then I'm also getting another 0. So again, F and G, I have to have one less value. Because those have lesser values, right? You get that. What is the issue now? No, not F. E and G. E and G, not F and G. Hmm. EI is AI minus. No, what is wrong here? Index 4 is out of bind for X with size 4. Get it, man. What is wrong here? So 0, 16, 16, it should have stopped here. I is AI. So F is working fine. Then this one is also not correct. To be E minus 1 here, I think. Then this one. Okay. Apurv, now do you see that E, F, G, and R are matching with the diagonal values? You there?
So in the second row, sir, I think
So in the second row, what's wrong?
no, sir, it's fine, fine.
Everything is okay.
Yes, it looks like yes, sir.
So if I implement this code with this code, we can actually represent. I can just delete A now, right? Can I delete A now and just represent A with E, F, G, R,
Hmm. Yes, sir.
right? Now I don't need A, right? I don't need A.
Yes.
Okay, now let's look at it. Now I'll show you how we can just simply remove A in the first place. Okay, What was AII? It was FI, right? I will write it here again. FF here. Now this will be E-1 because that is how it is, right? Because it was just a placeholder. It was nothing special there. You get that, right?
Yes, the thing is that we actually don't want to deal with a sparse matrix. We just want to define create three vectors, the diagonal and the other two subdiagonal vectors, and with proper manipulation, we just want to like solve it.
Yeah, because even if you define the sparse matrix, you're actually storing zero zeros in a lot of place. If it is a
Yes, sir.
large number, it will, that is the whole logic. See,
It
this
will.
code also works. This code also works, right? Isn't it?
Yes,
Now
sir.
there is no A. I'll show you. There is no A right now. I'll show that to you. So there is no A here at this point. Probably you get it. There's no nothing special to not get there. See, so you don't need to define the array there. But we could have defined the array and then do it. That's also okay.
Maybe it will take some more time, right? If the system is large, so this is much more clever way of doing things.
Yes, you don't need to just waste a lot of space.
Yes.
Yeah. At the end of the day, it's an algorithm. You don't need to spend too much energy into it. It's an algorithm. It's written somewhere. Now your job is done. If you understand what is going on, that's it. You don't need to get
Mhm.
into uh, details of implementing it. Okay. So I don't know. Are we left with any question there, or are we done?
No, sir. It's done, sir. Done.
Okay. So maybe, yeah, that implementation, we could look at what that implementation is. I don't really care too much into this. Okay. So yeah. Maybe if you have any doubt, let me know. I can try to show TDMA in the next class. Do you want me to properly show it?
I I'll also try on my own, sir. I'll try on my own.
But do you think I should, the next time we do it, should I cover these parts or what should we do?
Mm, no, this part is okay, sir. This part is done.
This part is
TDM,
done.
yes, sir. Yes, I think so.
Okay. But your problem was solved. You got your answer, right? Or
Yes,
it's
sir.
still
I got my
unanswered?
answer. I got my answer.
Okay, great. Fine. So Upur, we'll meet next time. It's 2 hours, so I'll stop now.
So
Let's
just one
continue with.
question before leaving, sir. Just one small question. I mean, I just wanted to ask you, like, which method do you employ more in all the flow problems, like Gauss Seidel or successive over relaxation or
I
TDMA?
don't. If you noticed, I didn't even care. I didn't even know how it solves my problem or not. I just simply call a library, and this
Hmm.
library seems to work on LU decomposition.
Yes, sir.
So a general
Uh,
matrix will require LU decomposition, but you can
but that
have
library works on any of those, would be based on
yeah,
those, any of those things, right?
yeah.
That's,
Essentially, our code will always be ineffective compared to someone who is writing a library. He is dedicating his time to write a full professional library. He will be
hmm.
also more efficient in his computation and space storage, like what do you call it? Time complexity and space complexity. So we actually don't need to write the everything on our own, especially in the time of ChatGPT when I just wrote a simple prompt and I got an algorithm. So see, this one works well and well fine, right? This works so fine. And don't need to do anything. Simply works.
That is okay. So actually, one should have the feel like how things are working
Yeah, yeah.
behind.
That's
That's the
true.
thing.
That's true. You can try implementing it, see why it works. That's correct. But at the end of it, it's an algorithm, and given how there is no theoretical background of what is going on there. It's an algorithm that works, and essentially it is Gauss elimination, right? So yeah. So okay, this is the derivation. Maybe I'll look at the derivation once. Next time, let me look at the derivation for this Thomas algorithm, and why we get that pseudo code at the end of it. We'll do that next time, so that some
I've
intuition
understood
is
that,
there
sir.
for us.
Yes, yes, sir.
Let's do this part of it. Let's see. I have to finish that finite element part of it also.
Yes, sir.
We couldn't do it today, but anyways, okay.
Okay.
Anything else, Purv?
No, sir. No, sir. No, sir. That's it.
Okay. Thank you, man.
Thanks.
Thank you.
Yes, sir. Thank you, sir. Thank you.